Okay, so welcome everybody to today's colloquium. It is going to be presented by Professor Viqar Husain, who is associated with the University of New Brunswick in Canada. He's also associated with the Perimeter Institute. He works in the general area of classical and quantum gravity. Uh, he has visited Pakistan several times. And we also are lucky to have one of his students as a faculty member here at LUMS. And right now, one of our recent students has just begun doing his PhD with Viqar. It's always a pleasure to have you over, Viqar, for a seminar. It's always a pleasure to hear you speak. The floor is all yours. Please go ahead.
So thank you for inviting me, and I always love talking to a Pakistani audience and sharing thoughts. So thanks for the opportunity. So I'll be talking about, as you see the title here, acceleration, relativity, and temperature. And I was very tempted in brackets to put art or artifice, and I left it at art. And you'll see why as we go through the talk. So the talk is in 3 parts. The first part will just be a review of pretty much everything I think everybody knows, but I think it's important to set the stage. And then I'll talk about the relation between gravity, acceleration, and black holes. And I'll tell you what all those 3 things are in the way that I think about them. And then I'll end with a puzzle after building this up. And this puzzle has no solution. And so you're invited to ponder this as we get there, and I hope we'll have time for discussion. All right, so let me begin then. So the first part is just temperature and radiation. What's the connection? By radiation, I mean light, and temperature, everyone knows what temperature is, sort of, except we have to say a few things a bit more precisely when we come to gravity and so on. So let me begin by defining what is a black body. And again, this is something you probably all know. It's a material object at some fixed temperature, non-zero temperature, that absorbs all frequencies of electromagnetic radiation and also emits all frequencies. And the simplest example of this is an oven with a small hole in it. And the oven is set at some temperature. This is what's called the heat bath. This is whatever mechanism heats it. This cavity is the oven, and you imagine a little hole in here, and you look at what light or heat is coming out of this. So you have a spectroscope and you measure frequencies and you ask how much energy is in there in particular frequency. Okay. So that's the definition of a black body. Oh, I should say, if it's okay with the host, if you have questions in between, I'm happy to answer. And the moderator can handle that. Rizwan, perhaps you can see if there are questions, and I'm happy to field them as we go through.
That's perfectly fine. We normally ask people to type questions, and I've already written that in the chat box. Okay. But if somebody wants to ask a question during the talk, you can raise your hand as well, and we'll take it from there.
Okay. So I'm happy with handling short questions. If they're long ones, then we can perhaps delay till later. And I get to decide what's a long answer and what's not. So we'll take it from there. Okay, so this is the definition of a black body, and there's this radiation coming out. The question is, how do we understand what's going on and what's actually coming out? So you go to the next slide. The actual experiment was done in 1895 by Wien. And here's the result of what is observed. It's this yellow curve here. And this yellow curve is an interesting curve. The vertical axis is energy density at a particular frequency, and the temperature of the oven is fixed. So this curve is for a fixed temperature, 1000 degrees Kelvin in this case. And on the horizontal line is the frequency. And so what's being measured here is the joules per cubic meter per hertz. And this is a standard kind of curve that we see in lots of places, and I'll give you an example of that. Okay, I'll give you more examples in a second. So this is the first actual measurement of the spectrum coming out of a black body. And it was literally an oven. Okay? Not quite what you see in your kitchen, but sort of like that. And so Max Planck found a formula that exactly fits this curve. This is the formula. And I should say that this formula was basically concocted with one assumption, and it was basically concocted to fit this curve right here. And this is what it looks like. It's got a few pieces, and I'll talk about each of the pieces in a minute. It's an energy density formula. It depends on frequency F. It depends on the temperature T. And here, what we have is T's temperature. So you can see where temperature occurs in only one place. Can you see my cursor on there? Yes, okay. Temperature occurs only here. K is Boltzmann constant. This should be F. F is this frequency here. And alpha is some constant. And Planck introduced this number H, which appears in two places, HF up here and HF over here. And so there was really no explanation for why this formula fits this curve. Now, there are numerous examples of this fit. This is not a one-off. If we look at the light coming from stars at different temperatures, we see exactly the same kind of curve. And slight difference, the overall factor is the same, but here we're measuring energy flux. So if you look at a blue star, which is at 18,000 degrees Kelvin, you get a curve like this. If you look at a yellow star, you get this. If you look at a red star, which is 4,000 Kelvin, you get this. And here it's plotted as a function of wavelength rather than frequency, but it's the same kind of a curve because we can easily switch between wavelength and frequency because we know the relationship between wavelength and frequency. So oven is one thing, stars are quite another, and yet we see the same fit. And it gets better. This is the cosmic microwave background from COBE data. And again, here the frequencies are much less, as you can see from the horizontal scale. These are microwave frequencies. And yet the fit is exactly the same formula. So from oven to stars to the cosmic microwave background, what's this formula doing? And that's really, an amazing kind of result that it's fitting so many things in so many different scales. This is the universe level scale. Oven is in your kitchen, and the stars are, of course, all kinds way out there. They all fit the same curve. So let's break this up into three pieces, this formula. The first piece is a prefactor, the second piece is an energy, and the third piece here is the thing we'll be interested in here, which is 1 over e to the hf over kt minus 1. The second factor here, as I say, has dimensions of energy. It just says that, okay, the left-hand side is energy, so the right-hand side has to have an energy factor. This factor here, 1 over e to the hf over kt minus 1, is dimensionless, and everything else is in alpha and f squared here. And the last factor is called this Bose-Einstein distribution. Planck didn't know it by that name. Planck just cooked up this factor just to fit the formula. So I'm just going to spend a little bit of time to see how we understand it, at least one part of this. And this other part here, this Bose-Einstein distribution, the explanation, theoretical explanation was provided by Einstein. This HF piece is essentially Einstein's hypothesis, which he elevated from Planck, that this is the energy of a photon, a frequency f. So the second piece and the third piece are really well understood. In fact, all three pieces are well understood. But I just want to say a little bit more so you carry away some insight from this formula in these three pieces. So the first question is, how do we understand this radiation? This is going back to the oven. And so the basic idea that people were using is we think of this as light waves inside a box. So let me lead you through that basic idea. And of course, you can find this in textbooks. There's nothing original here, but it's just useful to set the stage for what's to come later, which has nothing to do with boxes and lights in boxes, but maybe, who knows? So the first factor, and what's the first factor? The first factor is this thing here. We need to understand this f squared sitting here. And this idea that it's light waves in a box provides an explanation of that f squared. So the first factor comes from counting light waves in a box of side L. And if we think of a box as being one-dimensional, okay, it's just, it's not really a 3D box, it's a 1D box. And so we look at wave modes. Here's x equals L, here's x equals 0, and we ask how many waves, how many frequencies can you fit in here? And so, you know, from elementary considerations that these are the possible wavelengths. You can have wavelength 2L, L, 2/3 L, and so on. The corresponding wave numbers are just 2 pi over lambda. And so you've got lambda in the first line. So the possible wave numbers are pi over L, 2 pi over L, 3 pi over L. They come in units of pi over L. And similarly, the frequencies, which is just the speed of light divided by 2L here, which is just pick off the wavelengths, 2L, 2L, L, et cetera, et cetera. So you see the frequencies come in pieces of C over 2L for this box. So this is all very elementary. And now we can ask, what's the definition of frequency, or it's also called mode density? And that's easy to see. The mode density is simply the number of frequencies or the number of modes between frequency f and frequency f plus df. And that's just n of f df. And so since the frequency spacing is C over 2L, you can see that up here, it comes in C over 2L. N of f is just 2L over C in this 1D example, and it's actually independent of the frequency f. So we know what this NF is for the 1D case. Now, if we look at 3D, which is the world we live in, in the 3D world, we can have waves in each dimension, the x dimension, y dimension, and z dimension. And so the wave number is actually a vector. And again, the basic unit is pi over L. So we have the x direction, the y direction, the z direction, so that we see that the modes are characterized by 3 integers, nx, ny, and nz. And so the unit volume in K-space is now pi over L cubed. That's the basic box size in K-space. Therefore, the number density of modes in a spherical shell of K-space is, you take the volume of a shell, 4 pi k squared, and divide it by pi over L cubed, and out pops f squared. So that's the explanation of that f squared formula. So this is the f squared in the Planck formula, and actually this was well known before Planck. What was not known before Planck is this factor 1 over e to the hf over kt minus 1. Now I want to go back with this understanding and point out one other thing. What was going on before Planck was what happened after Planck. So here's our formula again. Before Planck, the third piece was missing. There was no 1 over hf over kt minus 1. And so rho f was proportional to f squared times f. So rho of ft was proportional to f cubed. And the problem with this f cubed was known as the ultraviolet catastrophe. It was known as the ultraviolet catastrophe because the energy density went as frequency cubed. And so for large frequencies, the energy density just grew as a cubic in frequency. And we didn't see that in nature. And so Planck invented this factor to cut down this high frequency mode. So you can think of this in modern terms as a kind of regularization of the ultraviolet catastrophe. This catastrophe, of course, didn't exist in nature, and the regularization is not an artifice. It's actually what we observe. So one way of looking at this Planck factor, the third piece here, is that it solved the ultraviolet catastrophe problem. Okay, so that's that. So we have a good understanding of this formula from multiple perspectives. And what's the message so far? So Planck introduced the idea that this h, in the f cubed, one of the f's is special. It's the energy of a photon. And he also introduced this formula. And Einstein later gave a derivation of this formula along with Bose. So the message so far in these introductory words is the electromagnetic signature of temperature is black body radiation, or in other words, these pictures that I showed you of the thermal spectrum, that's called the black body radiation spectrum. That's an important message. And here we understand everything. And now we're going to begin the journey where we get the same kind of a formula, but we understand very little. So I'm going to pause at this stage, see if there are any questions.
If somebody would like to ask a question, please go ahead, unmute yourself and ask the question. Does anyone have a question from the audience? Viqar,
Okay.
I think we're good to go.
Good, good. Well, this is textbook stuff. And so I'm hoping you all know this anyway. All right, so now we come to gravity acceleration and black holes. Now, the basic idea that led to the general theory of relativity is what Einstein called his happiest thought, which is the equivalence principle. And the equivalence principle says that locally, in a small region of space, that acceleration is equivalent to gravity. And Einstein's thought experiment, or his happiest thought, is illustrated in these two pictures. And on the left is a picture of somebody standing in an elevator and accelerating upwards with G. And the statement is, and this is local, the elevator can't be too big and the gravitational field can't be too strong such that it changes from one end of, say, 6-foot elevator, 6-foot wide elevator from one end to the next. So if you imagine yourself standing in an elevator that's moving upward with acceleration G, and you do some physics experiments like dropping things and measuring how long it takes to hit the ground and doing other experiments like that, then the result of those experiments will be identical to the experiments you do on the surface of the Earth. And that's called the equivalence principle. In other words, acceleration is indistinguishable from gravity in small regions of space. And this is what led Einstein to think of gravitation as really a geometrical phenomena as opposed to a physical force phenomena in the way that we understand electricity and magnetism. And this simple thing has lots of consequences. And here's one fascinating consequence that Einstein predicted. So if it's true that acceleration locally is the same as a gravitational field, then in an elevator, we can imagine what's going to happen. So here's the person on the left in an elevator going up, and a photon enters from the left side, follows this red trajectory, and by the time it hits the other wall of the elevator, photon's not going to hit at the same level. It's going to hit a little bit lower because the elevator has moved up slightly in the travel time that the photon took to go from where it entered the elevator to where it hit the other wall. And so to the person inside the elevator, it looks like, hey, the light just bent a little bit. So Einstein said, if his equivalence principle is true, then the same thing must happen when light passes a gravitational body. Otherwise, the equivalence principle would be false. And of course, that's exactly what was discovered in an experiment in 1919. And so that was the first verification, experimental verification of the equivalence principle. And the general theory of relativity is, of course, built on the equivalence principle. So there's another fascinating consequence. If gravity can bend light, it can also trap light. And this is rather easy to see. It only requires Newtonian physics. So if you imagine that the usual formula, you have an escape velocity to launch a projectile into orbit and beyond the Earth, imagine that if your body was sufficiently massive, that the escape velocity was the light speed. Then you write down this formula you're all familiar with, and you find that you find a relationship between the radius of the object, as we're assuming is just spherical, and the mass of the object. And this is this formula on the right here, which is an important formula. Now, such an object is called a black hole because light can't escape it. And it has a surface gravity just like the Earth. And of course, because light can't escape, but light can fall in, it absorbs all incident radiation. So in that sense, it's kind of like a black body, because black bodies absorb incident radiation. But of course, as we saw, black bodies also emit this black body spectrum. And we can't imagine black holes to emit anything because it's supposed to be black. But Hawking discovered in 1975 that in fact, when you consider a black hole in the environment of electromagnetic radiation, say, so, black hole is an astronomical object, and you can imagine photons whizzing around the black hole. So there's a black hole space-time, and there's matter in that space-time. So Hawking showed by combining the quantum mechanics of the matter, or the quantum field theory of the matter around it, around a black hole, that in fact, black holes not just absorb everything falling on it, they also emit radiation. And he found that it's exactly this formula that Planck discovered. So this is extremely strange, because a black hole is sitting out there. There's no heat bath, there's no oven. It's just a massive object sitting there. And so he found, among other things, that this temperature turns out, the temperature is an analogy here, it turns out to be proportional to the inverse mass of the black hole. What this means is that if you've got a really massive black hole, then its temperature is really, really tiny. And the smaller the black hole gets, the hotter it gets. And so that Planck formula that tells you how much energy is being emitted drastically changes as the mass changes. Same kind of shape, same formula, but those shapes are different depending on the temperature. So here he discovered that the shapes are different depending on the mass. So what I'm going to do now is, I know most of you don't know general relativity. So I'm going to give you a derivation of this Planck formula from the point of view of the equivalence principle without general relativity and without anything other than special relativity and acceleration and the Fourier transform. So let's see how that works. And then we'll just invoke the equivalence principle at the end and say, okay, if it works in an accelerating frame, I'm just going to invoke the equivalence principle, which we know is true because there's so much experimental evidence for it. And we'll transport that into Hawking's formula, just using the equivalence principle without doing the calculations Hawking did. So this is how it goes. So this is what I just said. If locally acceleration is equal to gravity, then we can calculate this result in special, can we calculate this result in special relativity for an accelerating observer? And the answer is yes. And we have to scratch our heads a little bit in doing all of this. So I'll take you through that. So let's start very elementary. Consider an inertial lab frame, Tx. We'll just do one time dimension and one space dimension. That's enough to make this work. And you can generalize to 3D if you want. In this frame, imagine that there's an object of rest mass m0. And suppose it has some trajectory x of t. Then its instantaneous momentum is just the usual formula from special relativity, mv over 1 minus v squared. And I'm using c equals 1. I'll put c back later because it's just a clutter. And so now we look at Newton's second law. And Newton's second law says the rate of change of momentum is mass times acceleration. We write it down. And that's what it looks like on the right there. D by dt of this is a, where a we assume is a constant acceleration. So basically in the lab frame, what's going on here is you're watching some object travel at this, on some trajectory x of t in the lab frame. Okay, so we want to solve this equation. So let's solve this equation. And it's a second order equation. And so you require some initial conditions. So let's say that at time 0, this object is at location 1 over a, and its initial velocity is 0. So you just integrate that equation, and this is the result with these initial conditions. You can use other initial conditions if you like. It just, you'll get a slightly messier looking thing, but I just want to keep it simple. So this is the trajectory. So this is the trajectory of a particle undergoing constant acceleration in special relativity in our lab frame xt. Okay, this is all hopefully all familiar to you. Now suppose you are the person accelerating, then your proper time tau is defined by this relation, because for you, you think you're the only person in the universe and you are still, and you're not changing, so your dx is 0. And only clock is ticking for you. So therefore, this is the definition of your proper time. And so from this, you can derive the relationship between the lab time and your own clock time tau. So lab time is t, and your clock time is tau. And yet we get another differential equation. So we integrate this, assuming that at time 0, you've set your clocks the same, set your wristwatches the same. So you integrate this, and you find a relation between lab time t and the time tau of the accelerating observer. Now you can do something else. You can say, instead of in the lab frame, the particle is parameterized by t and x of t.
Viqar, we have a quick question asked in the chat box. Why are you using this t of this initial condition of x of 0 being 1 over a? I thought you just said that it's just to make the equation look pretty, but maybe if it's something deeper than that, you can take the question.
No, there's nothing deeper than that. Everything I say is going to work if you don't use that initial condition. This is what I'm talking about is not dependent on the initial condition for the accelerating observer. You can have,
thank you.
Yeah, you can have the accelerating observers sitting somewhere else on the x-axis to begin with.
Yeah.
Okay. Yeah, so this is sort of the minimalist thing in the sense the formulas are nice. And nothing else of substance, nothing of substance is going to change if I change the initial condition. Okay, so what do we have? Let me just summarize. In the red equation on the bottom, we have t and xt. That is the location for the lab observer of this accelerating object, or accelerating observer, or mass, or whatever's accelerating. And I can just choose a different time coordinate, tau, and write that same trajectory with respect to the proper time, tau. All right? It's the same trajectory. Just, if you like, the curve is parameterized differently. That's it. But it's an interesting parameterization because it has a physical meaning. And the physical meaning is that this tau is the clock time of somebody who's actually on that accelerating trajectory. That's why it's a useful different parameterization of the same curve. All right, so what do we do with this? Now we ask an important question. How does a plane wave, again, I've put c equal to 1, simple plane wave, e to the I kx minus omega t in the lab frame appear in your accelerating frame if you are the accelerating observer. The plane wave is just sitting there, just floating around in the lab frame. The lab observer is looking at it, and you are the accelerating observer, and you're also looking at it. So what does it look like to you? Well, all we do is we say, oh, the accelerating observer has clock time tau, and I already know the relationship between t and tau and x and tau, so I'm simply going to stick it in this formula. So for x and t, I'm going to put x of tau and t of tau because I know those formulas. And then you can simplify this and you end up with this bizarre looking thing on the right-hand side. It's just a substitution. Okay. So if you like, what we have here is a plane wave in the lab, which looks completely normal. But to the accelerating, in terms of the accelerating coordinates in the lab of the accelerating particle, it looks really weird. It's e to the I omega times, it's got an a in it because it depends on the acceleration, depends on the proper time. Now, this expression on the right-hand side is interesting, quite apart from its bizarre-looking functional form. It's actually what the accelerating observer will see of this plane wave. That's what the accelerating observer will see because it's a function of the accelerating observer's proper time. Now, the accelerating observer, being a good physicist, is going to say, wait a minute, this is a bizarre signal. What is the frequency content of this signal? So if somebody gives you a signal and you're a good electrical engineer or physicist, you're going to say, okay, I'm just going to do a Fourier transform and I'm going to find out what's the frequency content of this. So let's do that. Okay. So when we do that, here's the Fourier transform of this crazy thing. There's e to the I capital omega tau. That's the Fourier transform factor. And then I've got this transformed, the wave is seen by the accelerating observer, the exponential of I omega e to the A tau over tau. It's an exponential of an exponential. Okay. So there's some interesting stuff on this slide. The energy in any signal is proportional to the amplitude squared. So we're just going to do a magnitude of f squared. Now this integral that I have there can be done exactly. And you can just do that as a little exercise. Don't look it up, just try to do it first. The result, after you put back the factors of C, is extremely interesting. It looks like a black body spectrum for magnitude of f squared. Never mind the prefactors, look at the black body formula. Now let's look at what went into this calculation. So all we put in is a plane wave. We transformed the plane wave into the coordinates of an accelerating observer. And then we said, what's the frequency content? So we took the Fourier transform and out pops the black body spectrum. Okay. And let's look at the exponential factor there in the denominator. It's got the omega in it. It's got the speed of light and it's got the acceleration. There's no h bar. There's no h. And there's no Boltzmann constant. And there shouldn't be because, those things aren't really involved in this calculation. But let's now make an analogy. Let's write 2 pi omega c over a, this thing here, in the Planck factor, and set it equal to h bar omega over kt. Then we discover an effective temperature through this analogy. It is an analogy. And that temperature is this. And so because we got the black body spectrum, we can associate, if you like, an artificial temperature just by making an analogy, and this is the temperature we get. So the temperature is linearly proportional to the acceleration, and it's got this strange factor out in front, h bar over 2 pi kbc. This is actually something that was discovered by Unruh around the same time as Hawking did his work on the black hole. Unruh did it on the accelerating observer in Minkowski space. And these were done in the context of quantum fields on a space-time. So in Unruh's case, it was quantum fields on Minkowski space. And in Hawking's case, it was a quantum field on a black hole background. So far so good. Any questions at this stage?
We have a question from the hall. I'm just going to pass around the mic.
Yeah.
Am I audible?
Yes, I can hear you.
Yes. I just want to ask that you mentioned that we just drew an analogy with the factor in exponentials and then just created this artificial temperature, this equation. So yes. Beyond this, is there any physical significance as to why we could create this analogy in the first place?
Well, this is part of the puzzle that is not solved. And I'll be coming to that. Remember, the third part of my talk is this puzzle. Does it go beyond an analogy? And this is why I said in the opening slide, art or artifice. And so I stopped at art, and let's just go forward with that. That's an important question, of course. Right now, at this stage, it's just an analogy. And when you do this with quantum fields, it's a bit more interesting because the quantum field already has an h bar in it. And again, although it has an h bar in it, you can ask who ordered the Boltzmann constant. And here I don't have an h bar and I don't have a Boltzmann's constant. I just have this formula that we got by doing this Fourier transform of this transformed wave. All right.
Okay, any question from the online audience or any other person in the hall? I guess we're good to go. Please go ahead.
All right, so I'm looking at the time. I think I want to finish so that there can be questions. So now with this result, let's come back to the equivalence principle. If the acceleration is not due to just an observer accelerating, but suppose the acceleration is due to the gravitational field of a mass m of radius r, then of course we know the acceleration is gm over r squared from Newton's law. Now for the black hole, there's a relationship between mass and size. This is basically what defines the black hole. And we already saw that before, right? The relationship between mass and size. It comes from this escape velocity formula, 1/2 mc squared is equal gm over g, big M, little m over r. Little m is whatever test mass you have. Cancels out, doesn't matter. So the relationship between mass and size is this r equals 2gm over c squared. So you take this r equals 2gm over c squared and you plug it into the first line and you find an acceleration. And the acceleration is c to the 4th over 4gm. So I'm going to take this acceleration and I'm going to stick it in this formula right here. Okay? And invoke the equivalence principle. So when you do that, you get this. The black body temperature of a black hole of mass m is something that depends on the mass, 1 over 8 pi m. And then it's got this combination of constants, h bar c cubed, g, and kb. Now, what's completely amazing about this formula is it's got every single fundamental constant of nature in it, including Boltzmann's constant, which is actually, you might say it's not a fundamental constant because it comes from really Boltzmann's formula for entropy in terms of microstates. The other three, you can say, okay, h bar c and g are fine. They're fundamental constants. But in a sense, you know, Boltzmann's constant is also fundamental because regardless of the kind of system you have in statistical mechanics, it can be particles, it can be a quark gluon plasma, it can be whatever, it's the same Boltzmann's constant. So although the origins are quite different, it's still fundamental. So that's why I'm calling it fundamental here. In fact, no other constants are like this. If you look at any particular interaction, like the weak interaction or strong interaction, those interactions are specific to those interactions, but everything gravitates. And so therefore, the gravitational constant is special and KB is special. It's more special than all the other coupling constants in the universe. Okay, so what's going on here? So I'm near the end. And so we come to the big puzzle. And the big puzzle is this. Is there something very deep about nature that connects the temperature of the most compact object in the universe, the black hole, with Planck's constant, Boltzmann's constant, the gravitational constant, and the speed of light? Or is this just an analogy and there's really nothing there? Now, in the derivation I gave, and so the moving parts of Hawking's calculation and the moving parts of Unruh's calculation, they're the same. The story is a little different because the story involves a quantum field, and so there's a natural entry point for h bar. And for me, for what I just showed you here, there's no natural entry point for h bar because that formula that I gave up here, this Fourier transform, there's no h bar anywhere. It's just an accelerating observer. And this formula just comes from an analogy. So in fact, the Hawking's derivation of black hole spectrum and the Unruh derivation naturally had the h bar in it. But still, the Boltzmann constant is a mystery, and the Boltzmann constant is through analogy. So the question now is, where do we go from here? So one of the big questions, and this is my last slide, so I'm just going to say a few more words about this. One of the big questions is that when we think about going back to the oven, there's this box, it's full of photons, and it emits the spectrum. And Einstein explained this Boltzmann factor, 1 over e to the h bar omega over kt minus 1, by using statistical mechanics. And he said, okay, suppose I have a gas of these photons in a box. He applied some statistical mechanics with the energy replacing, doing some counting for identical particles and replacing the energy in the Maxwell distribution, which is 1/2 mv squared by h bar omega, and he got that formula. And so what I'm getting at is that the formula is derived by saying that there are some microstates of the system. There's something inside that tells you what is temperature, and then from that you can calculate entropy and so on. So one of the big puzzles is, what are the microstates of a black hole? What is it that's causing this black body spectrum? And related to this is the question of, how do black holes form? Well, black holes are they didn't just appear and sit there forever as static objects. They're alive, and they're absorbing matter, and all kinds of stuff is going on. Hawking predicts they're going to evaporate by emitting this black body spectrum. But black holes really form from matter collapsing. And so matter comes in, matter collapses, forms a black hole. Presumably matter keeps evolving. And then what happens? And so one of the interesting things that happened earlier here, which we found, actually it's here too in this formula, that temperature is inversely proportional to the mass. So if black holes are actually emitting particles, then their mass is shrinking. As the mass shrinks, the temperature goes up. And in the very last stages, when the mass of the black hole is extremely tiny, the temperature is gigantic. It's in the gazillions of degrees. And so Hawking called his first paper on this black hole explosions, because as mass shrinks, the temperature rises, and there's suddenly a massive explosion. But there's a problem, and the problem is that this formula can't really be true everywhere, because we know that at some point quantum gravity has to come into play. If we take G, h bar, and c, there's a fundamental length, fundamental mass, and fundamental time, at which point general relativity breaks down. So this entire analogy I've described is probably going to break down at the Planck scale. And so one of the viewpoints on this very active area of research for the last 45 years is, what does quantum gravity have to say about these formulas? These formulas are not derived from quantum gravity. I didn't mention quantizing gravity in this whole talk, but it is necessary to understand what are the ranges of these formulas, if they're actually valid, or if it's just an analogy. But there's indication that it goes well beyond an analogy, and otherwise it would have been discarded much earlier, I think. So with that, I'll stop, and we have about, hopefully, a few minutes for questions.
All right, thank you very much. I don't know if you can hear the clapping. It's roaring in here.
Oh.
Okay. We can have questions now. Online audience. Okay, so we have a question from the hall. I'm passing around the mic.
Hello, Professor. Am I audible?
Yes.
Yeah, Professor. So it was a really amazing talk by your side. My question, or rather, I would say like an idea which came into my mind, is that essentially what is connecting all these constants, I feel like, is the not the idea of the like black hole, but essentially the singularity. Or so the idea which came into my mind was that if we go back in time and see the first singularity in nature, which was the Big Bang, as the universe originated from a singularity. And I feel like we will also find connection of all these constants at the time of the Big Bang. So I feel like it's the singularity which is connecting all these constants rather than the black hole.
Well, the thing is that the question is whether the singularity actually exists in nature. So as we know, before quantum mechanics, we didn't think that matter could be stable, because if the nucleus is positively charged and the electrons around it are negatively charged, and we know the Coulomb interaction has a singularity at r equals 0. And so if we look at trajectories of electrons in the vicinity of a positively charged nucleus, and we use classical electromagnetism, we know that the electrons would spiral in and hit the nucleus. And that doesn't happen. That doesn't happen because quantum mechanics removed the singularity. And so we think that, and there's lots of indication over the last several years, that when we apply quantum ideas to the gravitational field, the singularity will be removed. Now, quantum gravity itself involves 3 constants, h bar, g, and c. So that combination is expected in quantum gravity. The big puzzle is Boltzmann's constant. Who ordered that? And what's that got to do with the singularity in your what you're asking? But so what I would say is, in fact, the singularity, we don't think the singularity actually exists, that quantum gravity effects will remove the singularity. But the combination of h bars, g, and c are still there. And the puzzle for me really is Boltzmann's constant.
Okay, thank you. So we have a couple of more questions, but before I take the next question, let me just say that if for some reason this, and I actually should have said it at the start of the meeting, if for some reason this meeting gets hacked, I will shut it down and restart it. So everybody just join after a minute or so. So I mean, it has happened once. Luckily, it happened towards the end, and I should remember to always give this warning. So we can take a question from the online audience, somebody called User, who's also turned on his video. Please go ahead and ask your question.
Okay. Good night, Mr. Viqar Husain. I'm Pima from Indonesia, and I have 2 questions. The first regarding the singularity. We know that the black hole horizon has the coordinate singularity that is different from the center of the black hole. The center is the physical singularity, and the surface of the black hole is the just coordinate singularity. It is the problem of the choosing coordinates of the black hole. And my question is, how can the coordinate singularity can enforce the Hawking radiation on the surface? Does it have a relationship with either we choose a coordinate or a physical singularity or not? How about your view?
So in Schwarzschild coordinates, the singularity at the horizon.
Viqar, may I interject? I mean, I think we had a little bit of hard time understanding the question. If you could repeat the question, if you understood it.
Okay, so
it'll be of benefit to all. Thank you.
So the question is, the question is specific to a black hole metric, which I didn't talk about. The black hole metric written in Schwarzschild coordinates has a singularity at r equals 2m, the formula that I gave. And the question is, and the black hole has a real singularity at r equals 0, the center of the black hole. And so the question is whether, as I understood it, whether Hawking radiation has to do with the horizon or the singularity at the origin. And so Hawking radiation actually has to do with the horizon, because horizon is the curtain that makes it a black hole. And the fact that Schwarzschild coordinates are singular doesn't really mean anything here. The event horizon is a surface in the black hole, and that's where the relationship between the radius and mass that I gave exists also for the black hole.
Okay.
And the horizon is actually necessary. The relationship between R and M is necessary for everything I said. And of course, it's the root cause of what's happening. In the case of the accelerating observer, there's also an effective horizon. And that effective horizon comes from observing that when you have if you have an accelerating observer in special relativity, even if it's constant acceleration, the accelerating observer can never attain the speed of light. And that's what defines the horizon for the accelerating observer, because no matter what your acceleration is, you will never attain the speed of light. So if I go back to that trajectory that I drew here, that dotted line in the xt plane is sort of like an effective horizon for an accelerating observer. It's called a Rindler horizon, because Rindler first spotted this phenomenon.
Okay, great.
And
Good of you to join in from Indonesia.
yeah,
We have a question from the audience in the room.
Hello, sir. I'm audible.
Yes.
Okay, sir. In the slide, you have mentioned that we have a mass that is inversely proportional to temperature, right? So if we have, So if we have a very massive that what we have, so the temperature, the temperature in that sense, in that case, it will be rise. Okay. So anything. We have any notion or any signal, anything from the cosmic microwave background for these such kind of things? For a more massive, for a less massive, we have. For a more massive, we have many. It has a high temperature. What you mentioned that Hawking says that it is an explosion of of the black hole.
So if we look at the cosmic microwave background, the cosmic microwave background radiation is literally radiation in a box, because the universe is like this giant box and the radiation is sitting in it. And so it is the result of an explosion, the Big Bang. And the Big Bang, so this formula doesn't apply there. This particular formula is only for a black hole. Our universe, the singularity at the beginning of our universe as we understand it, right now, the so-called Big Bang singularity, is not a black hole. It's a different kind of solution to Einstein's equations that describes the universe. And so the cosmic microwave background is.
I'm not sure if I understood the question, but okay, so I have kind of like a tangential question.
Yeah.
Is there a black hole that is so massive that its temperature is equivalent to the black body, to the CMB temperature?
We haven't observed one. Well, I think it's a matter of plugging in the numbers. You can say, okay, suppose T is 3 degrees Kelvin. What M do I need? And you can just calculate that. I don't think we've observed such a thing yet.
Okay, we have another question over here in the room. I'm passing the mic around.
Yeah, I just had a question that at the end you mentioned how from all the constants, the Boltzmann constant was the most puzzling to find in this equation. So my first inclination was maybe this combination of the gravitational constant and Planck's constant would be the most confusing one. But can you elaborate on why is it that the Boltzmann constant specifically is more puzzling in the context of a black hole?
Yeah, so from my perspective, it's this. When we have special relativity comes with the speed of light c. And we know that all the relativistic quantum theories we have, for which there's lots of experimental evidence, have a c and an h bar in it. So to have c and h bar is no big deal. It's very familiar. Then when we come to gravitation, we have to introduce Newton's constant g. So from the fundamental theory point of view, we've got 4 big theories: strong interaction, the weak interaction, electromagnetic interaction, which are sort of unified now. And then we have gravity. And in all these interactions taken together, the fundamental constants are h bar, c, and g. And g is special compared to all other interactions, as I indicated, because everything gravitates. Everything doesn't have a charge, but everything gravitates. Everything doesn't have a gluon, has hadronic charges and so on, or isospin quantum numbers, but they do have mass, and anything that has mass gravitates, and everything gravitates, including photons. So therefore, G applies to everything, and H bar and C apply to everything that we know of. And so they're truly fundamental from the point of view of formulating Lagrangians and constructing quantum theories. On the other hand, Boltzmann's constant is something that comes from collections of particles, and we look at large ensembles and we calculate average properties, and that's where Boltzmann's constant comes in. Boltzmann constant doesn't come in at the microscopic description of matter, but H bar, C, and G do come in from the microscopic point of view. Boltzmann's constant comes in from large ensembles, collections of hundreds, millions of zillions of particles in a box, typically. And so this is why Boltzmann's constant for me is qualitatively different from the other three.
Okay, so we have two questions from the online audience. Among the online audience is a disgruntled customer. He's saying that Professor Viqar lied on the poster. Well, okay, I made the poster, but it's based off of your abstract. And he's saying that Professor Viqar mentioned some new developments, and I didn't hear any new developments in the past 45 years. So could you please tell us, let us know what's going on in the past 45 years? I think this question actually deserves a whole talk of its own, but it's actually my fault. I asked him to dumb it down to the level that people can actually understand. So I guess that's the reason that he hasn't talked about some of that. Maybe you want to add a comment to that?
Yes, I could show you a movie, but that would require some build-up. It's a recent paper that's coming out in Physical Review Letters this next week, probably, which would be one of the new developments. In that, what we show is a complete life cycle of a black hole. We take some matter that starts to collapse, and this is a quantum gravity simulation. And in order to show, I could show you the movie, but the movie would not mean much without the background. And I wanted to explain some things everybody could chew on. And if I go into describing a quantum gravity model in detail and show you the movie, it would actually take another talk, and it'd probably take more than one talk if I'm to
that was my feeling. That was my feeling.
Yeah. So I can just just to make this disgruntled customer happy, I can tell you what's in the movie. So
please go ahead.
The movie shows a clump of spherical mass that starts to collapse. It comes in and it forms a black hole. It keeps moving, and then the singularity is avoided. This mass starts moving outwards as a shock wave and emerges outside, and the black hole disappears. So it's a complete life cycle picture of a black hole, from gravitational collapse to singularity avoidance to bounce to the emergence of a shock wave. Exactly the kind of shock wave you see when an F-16 breaks a sound barrier, except this is a shock wave which signals the death of a black hole. So I hope that'll make him a little happy.
I hope it does, and if that doesn't, then nothing is going to make him happy. Usman, I hope you're happy. Okay, might I suggest that we take one last question, which has already been asked in the chat box, and then perhaps you can go to the movie, if that's okay with you, Viqar?
Oh, you want to see the movie? Okay, I'll dig it up and I'll show you. Yeah.
Okay, yeah, but there is this one last question. It is the temperature T of the black hole. Is it the temperature at the horizon, or is it for R equals infinity? Can you also comment on black hole firewall? question by Junaid, written in the chat box.
Okay, so the first question was what?
The first question was the temperature of the black hole. Is it the temperature at the horizon, or is it for r equals infinity?
So this is, so here, this temperature is the temperature of the black body seen outside the black hole. Its origin is the horizon. But if you're sitting outside the black hole, this is it's like you're sitting outside the oven and you're seeing what Wien saw back in 1895. If you're sitting outside the black hole will be emitting this thermal spectrum. So there's no radial coordinate here. So if you're sitting outside the black hole some distance away and you've got your measuring device to measure how much energy there is coming out in every frequency, this is what you'll see. You'll see a black body at this temperature.
Okay, so this is the last question that's going to be asked. Adam, please go ahead. Oh, he has 3 questions. No, you get to ask one.
Okay, I'll just ask 2 short questions. This relationship between temperature and mass, if you do the full general relativity calculation, does it remain the same or does it change slightly?
So this is exactly Hawking's calculation. This is exactly Hawking's formula for the temperature of a black hole.
So you get the same using the full general relativity.
Exactly. Hawking derived exactly this formula with every single factor in place.
Okay, fine. Yeah. And is there any observation that verifies this formula?
No.
Okay.
So I should tell you there's some interesting developments here. And that's part of the developments is a so-called black hole analogs. And so the kind of black hole analog I could go into a little bit of a story here is, can you construct things? Actually, the story is worth going into. So suppose we are thinking of a very still pond of water. And suppose you take a ring, large ring, and you plonk it on the water and you lift the ring up. What do you see? You see outgoing circular wave and you see an ingoing circular wave, right? That's what you'd expect.
Right.
Now suppose that the pond has a big sinkhole in the middle. And then you plonk your ring on the rings can be different sizes. So you plonk a ring on the pond and there's a little sinkhole in the middle where all the water is being sucked out. Now you can imagine that the circular wave going out will still go out and the circular wave that's going inwards will still go in. But there'll come a point when the outgoing circular wave can no longer continue to escape. It'll stop and it'll get dragged back into the sinkhole. So what this indicates is that you can imagine a sinkhole that's kind of like a black hole, which is preventing outgoing water waves from going out. And so that can be viewed as a black hole analog. And so people have been constructing black hole analogs in the lab and trying to see if something like Hawking radiation can come out. In other words, these are fluid mechanics models where you imagine the fluid flowing on some background, and the background is like the background of a black hole. So in terms of experimental verification, that's an ongoing research area with lots of experimentalists involved in trying to construct what are called black hole analogs. And you can Google that phrase, black hole analog, and you get lots of hits, and there's some popular articles on that too.
Right.
Okay.
Right. and there's been a lot of push, I think, towards using tools from quantum information on this side as well.
Yes.
So what do you think about that?
So I think tools are tools. I don't think they have informed the fundamental theory at all in any way. I think to really understand what's going on, you have to solve a problem like gravitational collapse with quantum gravity and see what comes out. That's what we did. That's what's going to come out next week in our paper.
Right. Okay.
So we don't use any tools of quantum information. We simply evolve matter using a differential equation and see what happens. And the differential equation is modified to include quantum gravity effects. And so, so concerning firewalls, I think you had a question concerning firewalls too, did you?
Yes, yes. The question was, can you comment on black hole firewall? Yeah, that was the question.
Okay, so I think if black holes did have firewalls, they would have been detected. The idea that the event horizon is the event horizon of a black hole is a completely global object. So you could be walking in a farmer's field and you can suddenly vaporize because you hit a black hole firewall. And so there's no evidence of anything like that.
Okay, great. Fascinating talk. It's a fascinating subject. Thank you very much for being with us. Thank you very much for sparing your very valuable time for us and for doing this really early in the morning. But any later than that, and it's sleep time for us. Okay. So thank you for that. Could you just show us the movie, and then we'll call it a day.
All right, so let me find, I think I have that movie. Let me just pull it up. Just give me a minute.
Please take your time.
Yeah.
Please take your time.
Had I known that question would come up, I would have had the movie handy.
Thank you, Usman, for putting everybody in an uncomfortable spot. Yeah, but thank you also. Now because of you, we get to see the movie.
Okay, so we have a movie coming up. Just give me a moment. I'm going to share that screen, a different screen. Okay, do you see this?
We can see it.
Okay, so I'll show you what the top frame is. This is at the beginning. The vertical axis, so there are two frames. The vertical axis is the energy density. The horizontal axis is the radial coordinate. That's the top frame, the energy density and the radial coordinate. The second frame is this quantity called theta plus. And again, the same radial axis at the bottom. And the red line is something which is called the apparent horizon function. So when you see this orange line cutting the blue line, that's a signal that a black hole has formed. And all right, I'm going to run the movie now. And I'm going to stop it in the middle at various points. Why is it not running? Okay, so, okay, I'll just slide it. This is a GIF, it's supposed to run. Hold on, I'm going to run a different kind of movie. I'll just run not the GIF, but the AVI, so.
Yeah, the AVI should definitely work.
Yeah, the GIF is not running. Okay, so we got the AVI. Now share screen. There we go. Okay, you see that now?
Yes, we see it.
Okay, so I'd say I'm going to run this twice. First, watch the blue line at the top, ignore the bottom thing, and then watch the bottom thing again. So. Okay, so what you just saw is, I'm going to run these frames slowly. So you got, look at the top line, you've got this matter moving in, and you've got this horizon condition forming right here. You see that the orange line is cutting the blue line, that's the event horizon forming. Now watch, this line, this first root stays fixed at 10 because this is a mass of 5 r equals 2m is 10. So this particular route, I don't know if you can see my cursor. This is the event horizon right here.
We see your cursor, yeah.
Yeah, and this other line that's moving inwards, the other route, so it's got two routes. The other route is moving inwards. And whoops, didn't want to go that fast. The other route is an inner horizon. The inner horizon follows the matter pulse going in, and then it hits r equals 0. Singularity is avoided. There's a bounce, and there's a shock wave coming out. That's the vertical thing here. Comes out. Notice that the outer route here remains at 10 throughout, and then there's no more horizon beyond this point. So what you've seen here is a density profile of matter. This is like a spherical shell moving in, bouncing back out, horizons forming, horizons disappearing, no singularity. And so that's one of the several movies we have. And we've tested this with different kinds of pulses, different kinds of data. We've tested it with double pulses, etc. And in every case, we get the shock wave coming out. And interestingly, we have a prediction. And the prediction is Hawking predicted the lifetime of a black hole to be proportional to the cube of the mass of the original mass that starts to collapse. Our prediction is not mass cubed, but mass squared. So for us, black holes live much shorter than what Hawking predicted. So now we just need to go out and observe shock waves coming
Observe
out.
a black hole and see how long it's going to stick around, yeah?
Yeah, or just watch a shock wave coming out.
Okay, lovely.
Candidates, you've seen these gamma ray bursts coming out and nobody understands them. And so maybe that's the black hole dying and emitting a shock wave. Anyway, the point is it's a precise calculation. And of course, every calculation has some assumptions. This has some assumptions. And the assumption to this is that there's fundamental discreteness at the Planck scale made from G, H bar, and C.
Nice, fascinating, fascinating. Okay, so while we have Professor Viqar with us, is there a final question that anybody would like to ask, or should we thank him and end the meeting? Is there a final question? Thank you very much. I don't see any other questions popping up. Again, thank you for a wonderful talk. We hope to see you perhaps in person at some point in the not so distant future.
Now, I'd like to do that.
Lovely. Goodbye. Thank you everyone for attending. Bye.